Hello guys, welcome back to my channel. It's the Caribbean Bookworm, and in this video I wanted to discuss a very interesting physicist from the past who you might have heard his name quite frequently these last couple of days, J. Robert Oppenheimer. And the reason why you might have heard his name is because there's a new Christopher Nolan movie that came out that is all about J. Robert Oppenheimer based off of this book, The American Prometheus, The Tragedy and Triumph of J. Robert Oppenheimer.
You know isotopes, and you know explosives.
But you can't tell us what you're doing.
Why would we go to the middle of nowhere for who knows how long?
For a year or two or three. It's about unleashing a strong force. Before the Nazis do.
And it's a very interesting book. I've started to read it. I'm not that far, as you can see, but I very much enjoy the book, and I'm at still the first beginning portions of the book at which you see him establishing himself as a professor at UC Berkeley and bringing quantum mechanics over to the US. But in particular, in this video, what I wanted to look at are three of Oppenheimer's main contributions to the field of physics beyond his well-known involvements as a director at Los Alamos for the Manhattan Project. So beyond that, there are three main contributions which Oppenheimer is associated with, one in which he is not particularly famous for, and two others which he is particularly very famous and much deservingly so for. So without further ado, let's start with one of them at which he is well known for, and that is the Born-Oppenheimer Approximation method. And this is a tool that is particularly one thing which set off the field of quantum chemistry, and it is particularly one thing which Oppenheimer developed with his PhD supervisor Max Born when he was studying at Göttingen in Germany for, of course, his PhD. In Göttingen, Oppenheimer got to refine his skills as a theoretician and basically became more and more exposed to the field of quantum mechanics and interacting with people who were later went on to become some of the most important figures in theoretical physics, such as Paul Dirac and Werner Heisenberg. In principle, one of the main contributions Oppenheimer made in his early days is this Born-Oppenheimer approximations. What it is in essence a very elegant way of describing what wave functions for the electrons of a molecule actually does, while not taking too much into account what the nuclei of all of the atoms in that molecule actually does. Because when you think about it, in quantum mechanics, when you're describing a single hydrogen atom, and hydrogen by itself can be very, very complicated, you're describing basically the quantum mechanical system that is a proton and an electron and all of its angular and radial components and how that plays into a role for the Schrödinger equation with things like spherical harmonics and such. Now, those who've done quantum mechanics know how hard and painful it is to actually do these calculations and derive these things from scratch. So this becomes even more tasking when you have many body systems, which you can think of as being the case when it comes to molecules. Like in molecules, you don't have just one proton and one electron, but if it was just a single electron, you have now many other protons, and not only that, but you also have many other electrons. So you can imagine that describing meticulously what happens quantum mechanically is a challenging task. And this is where the Born-Oppenheimer approximation comes into place. As in density functional theory, or shorthandedly DFT, the nuclei of the various atoms in a molecule are treated as this fixed, you could say, potential around which the electrons, basically, which you're describing, kind of go about their business and do their thing. So in principle, the total energy you have describing the, you could say, the electronic properties of a molecule would be described by things like the rotational energies, translational energies, and all of these different things. So it is a very useful tool, especially for people doing calculations with material science, some areas of chemistry, and even all the way till areas like drug development in pharmaceutical sciences. A lot of people in these sciences use softwares which perform DFT calculations for molecules which they're interested in making with particular properties. So basically, these DFT calculations have very practical use nowadays, and a lot of the calculations rely on the foundation, which is the Born-Oppenheimer approximations. And I think for this reason, this contribution of Oppenheimer's is one that is very close to a lot of these people's, you could say, heart, and it's just something that we work with very regularly. For me, however, the second thing which J. Robert Oppenheimer worked on, which I find to be particularly close to my heart, is his work on neutron stars. And in particular, he worked with Richard Tolman and Volkoff, a Russian physicist, on what we currently know to be the Tolman-Oppenheimer-Volkoff limit for stellar objects. And what this is, or shorthandedly the TOV limit, what it is in essence an upper limit at which you can have the mass of a neutron star to be. So the general gist of things goes that in the stellar evolution scale of things, when you look at a star at the end of its life, it can go supernova and you can have its inner core collapsing, and this collapse happens to such an extreme degree at which you have atoms in the core of the star compressing to such small, you can say, regions and such high temperatures and pressures that you can have things happening with electron degeneracy, and from this you can have things like white dwarfs. And white dwarfs themselves are very interesting stellar objects, but there is an upper limit at which, theoretically at least, one can have the mass of a white dwarf to be, especially a static white dwarf. And this upper limit is the Chandrasekhar limit, beyond which, if a stellar object is beyond the Chandrasekhar limit, it continues to collapse under its own gravity up till the point where it becomes something like a neutron star. But neutron stars have their own upper limit, and this was the calculation which Tolman, Oppenheimer, and Volkoff worked on. And this upper limit basically holds for a non-rotating neutron star, and for this non-rotating neutron star, if it surpasses the TOV limit, then it collapses beyond the neutron star and becomes either something like an exotic state of a star, like if a quark star happens to exist and they find signatures of it out there, or it collapses immediately down into what we know to be black holes. And the fascinating thing about the TOV limit is that it provides an astrophysical explanation as to how one could get black holes out there, how one could get stellar black holes, at least in a very natural and astrophysical sense of things. If it wasn't for this, black holes actually would just remain in the realm of just this theoretical curiosity, at which if you solve the Einstein field equation from the theory of general relativity, you get a solution which describes this weird geometry of space-time. But the TOV limit describes how one can get this astrophysically, and that's very fascinating. And an open question is whether there exists an equivalent for white dwarfs, and it is a very niche, interesting area of research. But this is the reason why I really like this particular aspect of things that Oppenheimer worked on. I didn't want to leave it up just to those two applications. I wanted to talk about a third one, which might be less familiar with a lot of people, but this entails his work on particle physics, and more so in particular on quantum field theory, as Oppenheimer was someone who was very interested in just quantum mechanics in general. And in principle, this entails his work regarding the lamp shift. And to explain what this is, we have to look again at the hydrogen atom, and particularly what happens to the hydrogen atom if you expose it to a magnetic field. Now, the hydrogen atom, if you know anything about, for example, chemistry or just quantum theory in general, you know that there exist different quantum numbers, basically, which describes the electrons in an atomic system. You have the principal quantum number, which describes more or less the general energy levels, and you have things like the angular momentum quantum number, which describes the different orbitals which you can have in atoms, like the s orbital, the p orbital, d orbital, etc. If you look at the energies of these orbitals, like I will put a picture of the diagram right there, and you look particularly, for example, at the p orbital, you have basically at one energy level, you have the different p orbitals which you can have. But when you expose something like the hydrogen atom, or a lot of atoms to that extent, to a magnetic field, what happens is that these energy levels for this p orbital, for example, would shift, and you would have basically that one energy level would split into various energy levels, and this is what is called Zeeman splitting. It's a very interesting phenomenon, and it is something which is particularly weird about quantum mechanics. It basically tells you that if you perturb, as one would say in quantum mechanics, if you perturb basically the you could say the orbitals of an atom, let's say a hydrogen atom, by introducing something like a magnetic field, some energy levels lose their degeneracy. So it loses that sticking into the same energy level type of thing which they have. And you have the splitting effect of the energy level. So there would be a measured energy difference which you wouldn't otherwise have in an unperturbed quantum system. Now, this was experimentally confirmed, and there's an analogous thing in the case of which the you could say in a hydrogen atom, the electron experiences when interacting with an electric field. And you can imagine this definitely to be the case, as for example, the proton has an electric field and the electron itself has its own electric field. So there will be some sort of self-interaction happening there. And the analogous of the Zeeman splitting is what is known as the lamp shift for this same effect, but with the electric field basically causing it this time around. However, one characteristic thing of the lamp shift is that it is very, very small compared to the Zeeman splitting which you would otherwise have with a magnetic field. And also, the thing which Oppenheimer worked on was that he noticed that the energy difference which you would get with the lamp shift actually, at least calculationally, should diverge onto infinity. It should give you infinite answers, which basically led him to believe that quantum electrodynamics, so this theory of quantum mechanics which kind of incorporates the electrodynamics, wouldn't be a thing. There wouldn't be some sort of unification of quantum mechanics with Einstein's theory of special relativity and such. However, even though, at least by pen and paper, there's nothing wrong with Oppenheimer's calculation, he did miss some subtleties about the theory as well as some of the experimental evidences which were later to be pointed out. In particular, he was using old-fashioned perturbation theory, and for that reason he was getting these divergences of the lamp shift. But also, there was the simple fact that the lamp shift was discovered experimentally in around the late 1940s, and this even yielded the physicist Lamp a Nobel Prize basically in 1955. So in essence, the way this was explained experimentally was through renormalization, and this is something that physicists like Schwinger, Feynman, and some of these other big names in quantum field theory developed. And it basically took into account that this self-interaction process in which you have this quantized electromagnetic field, and by the way, quantized sounds like a fancy word, but you can think of it in terms of, for example, if you were to have just a classical picture of an atom in which you have a proton and electron spiraling around it. At least in the picture of classical electrodynamics, this electron should spiral into the nucleus of the atom, as this electron would radiate away electromagnetic waves and would therefore basically spiral into the positively charged particle. But because of the process known as first quantization, in which you have basically Niels Bohr's model of the atom, basically you quantize the energies which the electron can have, you prevent this spiraling inward of the electron into the atom. And this process quantizes basically the energies which these electrons could have. Very similarly, in quantum field theory, you have that entire fields, such as the electromagnetic field, could be quantized, and the quantized electromagnetic field would yield to objects known as virtual particles. So basically, for example, the interaction between two charged particles is described, instead of this classical picture of if I have two electrons and I bring them closer, instead of their repulsion being to do these like asymptotic type of field lines going out, it would be due to the interaction of the virtual particles. So if you bring two electrons together, one particle would emit a virtual photon to the other, and due to some conservation quantities, like the conservation of momentum, for example, they would repel each other. Now, the one subtlety about this thing is that in quantum field theory, this virtual photon, or in any case, just force-carrying particles, such as you have with the strong force to weak force, and potentially maybe with gravity, these virtual particles are in principle mathematical things which you use. So for example, when you're describing two electrons coming close to each other and then repelling each other, the interaction, or the way at which a virtual photon was emitted and the way it interacts with the electrons, that is in principle unknown. We do not know what actually happens. We just know that, for example, when you bring the two electrons together, there is a foggy process that happens, and then you get repulsion. And mathematically, the way people that work on quantum field theory do this is they sum over all of the possible ways in which the virtual photon could interact with the electrons. And this leads to a process known as renormalization, at which, even though you have divergencies going on to infinity, such as the one which Oppenheimer found, because you sum over many other infinities, some of these infinities kind of cancel out each other, and you get basically a finite answer which predicts what you would measure in certain experiments. And basically things like the experimental evidence for the lamp shift kind of prove that renormalization that have some meaning in physics, even though it sounds at least mathematically very like a very smugly process in which you're sweeping infinities under the rug. So this is a very interesting avenue which Oppenheimer tried to tackle as well, but perhaps with an approach which was not as novel as what was needed to properly flesh out this new model of quantum field theory. So I hope you found this video interesting, and I certainly did, to know all about these things which Oppenheimer worked on. And of course there are many other things which Oppenheimer worked on which I didn't mention, as they're just a lot, and he worked on various couple of things even during the Manhattan Project. So if you found this video interesting, do let me know in the comment section below, as I'm curious as this more short and hopefully fast-paced video was of your intrigue. I hope you guys are having a great day, and I hope to see you all very soon. Bye.